how it is, but it do.
But it do be, yeah. Okay, here is a special case for the differential equations. And I'm not gonna do the slope field part of it because honestly, those are beyond easy for us right now. We will do
You get our
the,
quiz back. so.
yeah, I will. I'm gonna go over this and then I'm gonna take Chelsea out so she can do her quiz and then we're gonna go over the quiz. Even though we don't really, those of you here got hundreds on it. I'm not sure how much of that was y'all and how much of it was Michael, but we'll go over it so you see what you did. This is a special case.
I have basics, I just have problems.
And it's more in the wording, okay? So let's get used to the way this one would be worded and how you should be interpreting this problem. So here's how they would verbiage it. All right, the rate of change of, and then they would insert something, so population, cost, whatever. So the rate of change of thing, whatever that thing happens to be, is directly proportional to the amount of thing present. Okay, those keywords, they're directly proportional to the amount of whatever that thing is present. Think, all right, in practical terms, if you've ever worked in food industry, I know when I waited tables, I had to, we made a trash can of tea every night, I mean a vat of that stuff, and then in the beginning of the night, the stuff just pours out, like a related rates problem, it comes gushing out, but as the night wears on, it comes out less slowly because there's less pressure. So the amount that's in there directly affects how fast it's moving.
No,
Okay.
that's not a really good deal.
It is, it's a great related rates problem,
You're
yeah.
making me hungry.
I know, right? Oh, yeah. So here's how the math looks. The rate of change of something, so let's call it dy dx. Okay, that is the rate of change of something. We could also use dp for population, they like that one a lot. We could use dt for time. But all in all, you got some derivative, call it dy dx, or dp dt, or dx, or whatever. Directly proportional to the amount of thing present. All right, this is the derivative of some function y, and that derivative is directly tied to the original function y. So this right here is how we would interpret this sentence. Okay, the rate of change of something is directly proportional to the amount present. Direct variation from algebra 1 looks like this. As one thing goes up, another thing goes up to match it. Think about a salary. If you get paid $10 an hour, you work more hours, you get more money, kind of thing, all right?
You get more money, right?
Yeah, well, but it's a linear thing, for the most part, it's a linear thing. We are taking that linear concept and translating it to a calculus idea here. Okay, so whenever you see this sentence, this is exactly how you should think of the problem. Maybe insert the right letters. So if they say the rate of change of a population, they would probably say dp, and directly proportional to time or something like that, and you would do dt, but the letters are kind of whatever. All right, here's the part that you can recreate over and over again if you don't get it. But when I get to the finish line of this, you should say, all right, when I see these words, I'm gonna jump straight here. So let's go. Separate your x's and y's. So I'm gonna bring the y down here, and I'm gonna bring the dx up here.
That was a good.
And I'm gonna go ahead and leave the k on that side. It's kind of irrelevant, but it's easier on the right side. Take a couple antiderivatives. The antiderivative of dy over y is one we should recognize, natural log absolute value of y. The right side, okay, don't get confused here. K is not the variable, k is just a constant. So the antiderivative of k is just going to be kx. All right, I'll slap on a plus c here. I am going to start numbering these because they haven't given us an initial condition just yet. Also bear in mind that we technically had two C's, one over here, that we then combined together to get one C on this side. So now the game is, let's solve for y. Okay, pretty easy thing to do, so we're gonna exponentiate, like so. The e and the natural log cancel, I get absolute value of y. Really important to have the absolute value there. E to the kx plus c1. All right, if you will recall from algebra 2, if you have the same base with different exponents there and you're multiplying, you add the exponents together. We're going to work in reverse. So if I was adding the exponents together, that means the original problem was 2 multiplications. Okay. So this would have been absolute value of y equals e to the kx times e to the c1. This part right here, C1 just represents a random constant. It's some random number I do not know. If I do E, which is a number, to a random constant, I just get a number, okay? So we will call that
Constant 2, I mean C2.
constant 2, C2 times E to the kx. And then last but not least, we'll deal with the absolute value. This technically means that we could have had a positive or a negative, so when we took the absolute value, we got a positive. So this is what we're looking at, plus or minus C2 e to the kx. But it gets even better. C, being a random number to start with, whether it was positive or negative is irrelevant. When you make a random number positive or negative, it's still just a random number. So, that's what we get. And I'll go ahead and call it C, just because we're not numbering them anymore, we found the constant. So when you see these words, you can do all this, or you can jump straight here. Okay? And it comes up enough that you may want to have it memorized. For you Algebra 2 junkies out there, this is continuous interest. The
Isn't
per
it just
P
something?
e to the RT,
Yeah, P.
that's the way y'all saw it back in Algebra 2, compounding interest continuously, which is where we get this from. Because, again, that makes sense, the rate of change of it is dependent on how much you have, so the more money you have, the faster it actually grows. So there's,
It's actually cool now, you never understood why there was an E in the problem, but now you do, because you took the antiderivative.
right.
You
And
took
the E part,
antiderivative, and then you had to get the E there to get rid of the natural log that you had, which is actually pretty cool.
yeah, yeah, and the kids always ask, you know, why is that E, why that particular number? And in Algebra 2, you can tell them because of Euler's limit. Euler found E, the fact that E itself is an important number by doing this. He took the limit as n went to infinity of 1 plus 1 over n to the n. That comes up in your compounding interest problems, not continuously, but if you compound it like 2, 3, 20 times a year, you just let that go to infinity, and this part of the formula gets sucked out, and that becomes E. That's how he came up with the number E, or where he was heading when he came up with it.
So it's just that.
That's E. Yeah, if you actually do that and let n go to infinity, you will get E
Oh, just level off it somewhere?
to E.
Yeah.
2.71828.
Okay.
Okay, so there's my little teaser for, this is the only case I've ever seen that they use repeatedly, so it might be nice to know it. If you don't have this memorized, it's really not that hard to recreate it. Irritatingly difficult, or irritatingly time consuming, but not that difficult. My guess is somebody would have forgotten how to split these two guys right here.
So how do we get pi? That's how we get E, but how do we get pi? I guess.
Okay. Well, you've always been told that it is, you can fast forward to this if you want to. The question was, how do we actually get the number pi? This was E, equals E. I might have erased it. Where do we get pi? Okay. You've been told that it is the ratio of the circumference to the diameter of a circle. So if I take the circumference of any circle and divide it by the diameter, I get pi. The problem is, in order to get the circumference, you had to know pi in the first place, which is the tail wagging the dog. So we have to actually figure out the pi itself. Where did we get that? Alrighty. Consider, if you will, the unit circle, or any circle, doesn't really matter. Okay, and imagine I put, starting using this as my baseline, I'm going to put an equilateral triangle right here. Okay, now what is it about an equilateral triangle that makes it equilateral?
All three sides are.
Three sides are the same, which would therefore make all three angles the same,
So
and
those are all
these would all be
60.
60 degrees. Okay, since we don't know what a radian is yet, okay, 60 degrees. How many of these, if I were to start stacking triangles end to end, how many would it take to get halfway around the circle?
2.5.
Try again.
Half.
I'm describing it badly. If I were to take one triangle and then flush up another triangle beside that, and then flush up another triangle beside that, it would take me three triangles. Okay? 480 degrees.
Okay. And
You with me so far?
Yeah.
All right. Now, this gets into what exactly a radian is. Now what I want you to do is take this equilateral triangle, all of them, and I want you to pinch it right here so that this side right here buckles out, okay? So that it starts to pop out. And I want you to let it pop out to a point where it fits smoothly on the circle. So not too much, not too little, but I want you to pop it out so that it fits exactly on the circle, okay? So we'd be looking at a pie piece that is something like this.
But now it's not 60, it's something small.
Something smaller. All right, now this side and this side are still the same, and this buckle is the same, all right? But it does pinch the angle. The angle itself, not that you need to know this, is roughly 57.3 degrees. Not that you would ever know how to come up with that, but there it is. All right, how many of these would it take to go halfway around the circle?
3 and some change.
3 and some change. How much change?
That's the one at the end that we get.
1, 4, 1, 5, 9, 2, 6, 5, 8. That's pi. So it takes 3 and something of these to make it halfway around. That's where pi comes from. Pi is pi is that many radians. This is a radian.
Uh-huh.
And so it takes 3 pi radians to make it halfway around the circle, 2 pi radians to make it all the way around the circle, so 2 pi times r gives you your circumference.
So, kind of like 180 divided by 3.7, 57.3.
Yes. That's 3 and some change. Yeah.
Okay.
That's where we get pi from. How many radians it actually takes. And nobody, kids are like, that's pi over 2, whatever, but they don't understand it's pi what? Pi is not just a number, it's a qualifier. It's pi of this, pi radians. That many things to go around. And the great search was on for thousands of years to actually come close to what that extra little chunk was. That 14159. Computer programs, when they calculate pi, if you were to ask it what pi is, it doesn't have that number memorized, it's actually doing a little formula. I think it's got a whole bunch of secants. The formula itself is kind of long, like 3 or 4 parts to it, but it,
Not as long as pi.
not as much pi. Yeah.
See, that's what I want to, like, a formula, like how do they solve for pi?
I think, I'm trying to remember what they do, I think they actually set up a secant. Don't quote me on that, I'll look at the computer, I'll go Google that or something, but I wanna say the formula has a couple of secrets in it, don't ask me why.
I wanna do like the first, like, it'd be fun to do like the first couple numbers.
That's how they actually field test a lot of brand new computers. They ask it to calculate pi, and then they see how long it takes it to shut down. When they make new processors, that's what they're trying to do, is to see what kind of load it can handle before it overflows, before it shuts down. Or overheats, either or, so.
So I should just go home and make my computer show front back.
Yeah. Now, what your computer will do now is just give whatever digits it is, because it's been programmed to cut it off, but when they make a brand new one, they take the kickstand off and they just say, all right, what's pi, and then they see how long it takes it to shut
I
down.
don't want it to shut, I want him to see it. I don't like the computer anyway, I'm getting a new one.
Yeah.
That'd be a fun way to break it.
All it would do is actually just shut down, then you can turn it right back on again, so it's not.
I was hoping to break it.
It might actually overheat. Some of them, in the early stages, they overheated because they were just working way too hard to try to
And
figure
then
it
they're
out.
just like liquid cooling,
Yeah.
and you're like, overheating, what's that?
Are we doing that practice AP thing this week?
I wanna see, oh, that sounds,
Or is that next week? You said we were gonna do a practice test.
I want,
I would love to do it Thursday and Friday.
Okay, then I gotta make sure to take some Advil before
Yeah,
then.
Thursday and Friday are the days that I have set aside. That would be fantastic if we
Alright.
could do that. I really don't think we need to go over the test that much, okay? So I think what I can do on the test will take us maybe 10 minutes, and then the rest of it is practice AP time. We'll talk more about that.
if they put in liquid cooling, could it boil the water for liquid cooling? That'd be so cool.
Because that has nothing to do with, well, okay, the liquid cooling isn't just water, it's,
Alright, but I'm saying like if you just put like,
you can boil anything, you get it hot enough.
like, I'm just, not liquid cooling, but I'm just saying if you pretty much put your like computer in water, but not like, made so
Right.
it worked, and just like made it on pie and just boil the water.
The trick would be to keep the computer running long enough to actually boil the water, because at some point it would shut down, it would lock up and shut down, so you have to keep it hot, but not so hot that it shuts itself down, but then you have to make it hot enough to boil whatever liquid is there.
Dude, that's so cool.
That's why they make liquid cooling the way they do, so it doesn't
Boil.
melt the computer. All right, cool, there's that.
That's so
Now,
expensive.
you. Let me give you.
Leave my classroom now! Away with you. You done.
Yeah. Okay, this was a practice problem we did in class. You can get the answers from somebody. This week's quest. I know you're excited about that. And then, this is the quiz you're gonna do. Exciting. No calculator, it won't help you. Yeah, it won't do you any good. It will not help you.
It will not.
Yeah, not one lick of good.
Whole point is that not calculated because it's.
Yeah, it would definitely be a non-calculator. Okay, let's go over the quiz. Again, more for the fourth blockers. Here, Michael, Amber, okay.
First time.
Oh my god.
You too.
It's never happened before.
It's funny, the people who were actually no Graham was messing up.
Y'all are so funny when you do group quizzes. I think the fourth blockers actually work together.
Did Graham do good?
I think Graham missed a point, he missed a minus sign.
He did it all by himself.
He missed 1 point. He missed a minus sign and his slopes were not, he didn't alter them enough.
Okay. He did it.
I tried very hard. You see my little
Yeah,
racing to.
y'all's actually, this is a fantastic
I
quiz.
take them and I try to make it as close as I can, and then after drawing, I'm like, nope, okay, gotta fix something.
Yeah, it's irritating, but, yeah.
Easy. Easy.
All right,
The
so-
OCD kicks in.
Here we go.
I learned-
So, go ahead.
That's fine.
I'm writing, go ahead, Tom.
I learned the word, the Icelandic word for game. So it's katska. So, because someone was saying easy katska, and I'm like, what? Like easy game. I'm like, oh.
Just Just don't
Easy
think
cut.
too easy. All right, let's go through this. The slope field itself I thought was relatively nice. Thankfully, nobody really got confused with the negative stuff. Honestly, it was the actual slope itself. The positives and negatives y'all were cool on, but by y'all.
It's just hard to adjust it.
Yeah. And that's really it. You just need to make it look more or less slopish than the one that came before.
Like I come out of, I've kind of run out of like ways to adjust it before it looks like it's one.
Yeah.
Or like straight up.
If you can, and y'all should have like IDs or driver's licenses or something like that.
I use my phone for some of them.
Just, and kind of aim for that, if I have to have a slope of 1, I'm gonna aim for that dot over there and
That's kind of
kind
what I
of
did. I
make
was
it look
like,
like this.
okay.
So we have,
Because my lines kind of got thick and I was like, I can't do this.
It's like one's a 45, half is like a 22.5 angle.
right.
Two
Yeah.
is
Alright, so you should have had horizontals going this way and horizontals going that way. That was what the point if you got all the horizontals, that was good. And then you had this slope, I think, if I remember correctly, was -1, or these were the ones, so this was a positive, no, wait a minute,
nope,
these are the 1/2s.
yeah,
That was a 1/2,
there's only one.
that was a -1/2. These were the, that was the one,
Oh, yeah.
there it is.
And like when the ones up top.
And notice it just needs to be noticeably, more steepish than that one. This one I think was a 4,
Yeah, I think one was like a 2 or something.
and this one ended up being something like a 2. So just notice it's not right.
What does this thing look
And then I
like?
think the other one
Huh?
was a 2.
What is this?
The graph looks like, I'll show you, because once you get the y equal, if you see the y equals, if you wrote it the way I
Oh,
wrote it,
yeah, yeah.
it's very obvious what this thing is.
How'd you, 'cause I wrote it,
The way y'all did it, y'all left the 1/4 on the bottom, and it
oh,
didn't
she didn't.
quite,
Oh, one point is on the bottom.
yeah.
Thank you very much.
She didn't.
I just mashed it all together.
Oh, I thought you took it off.
No, my 1/4 is there.
Oh.
I think you factored it out. Y'all didn't factor it out, y'all just left the one, I mean, it was,
Because it bothered me because it looked messy.
yeah, it did me too. So there's the first one.
Not my
And,
fault.
okay, here's what I'm thinking of this slope field. It looks like we have a horizontal tangent right here,
Yeah,
okay? Whether or not that's a horizontal line, I don't know. I mean, if we actually stick in y equals 0, we would
that
get
guy
a
looks
horizontal line.
like, this is a hump up here.
Right, so this is what it is, and the further out I go, the more pronounced that hump is gonna be. So if I were way out here, the hump would be really tall, like that. The closer I am to the x-axis, the hump is small. So depending on what point you pick,
E to the
it
x squared?
just looks like a hill. What's that?
E to the x squared?
Either the -x squared is actually really, e to the x squared is
Oh,
just
yeah.
How do you know,
skyrockets.
whenever they ask you to like draw on these sometimes, like how do you know that?
I was just thinking of that.
Where to start?
Like, I don't know, I feel like
Oh,
if
yeah,
I
yeah, yeah.
started over here, then it'd go this way, but if I started over here, then it'd probably go up. And it's just-
Right, okay, so here's what I'm thinking. If this were a dot, they didn't ask you to do this, but if they had,
You just start wherever they.
wherever they give you to start, let's say right here. Alright, see, to me, that already looks like it's on the downward slope. Here, if I were to do this dot, it looks like I'm still climbing. This one looks like I'm actually leveling out and I stopped climbing back here. So I would imagine this little piece is probably on this leg of it, and then it'll do something like that.
Until it was on, yeah.
But if I were to pick a point like this one, it looks like I'm still on the upswing, and it would probably curve somewhere else up here,
Yeah, very rapid.
okay?
Mhm.
So, but they all kind of look the same, this molehill in the middle, and then it tapers off on the outside.
Okay. Cause I was imagining the one that's kind of like
I
flat,
was
and
just
this
thinking
side was
either
imagining going
next-
this way.
either
I actually
And
never
the
think
closer,
of it.
that is a very good example of
Because it
either
has the
negative x
horizontal
squared,
extension.
yeah, but there are a couple of others that also have that same feel to them, one of which we will see in just a second. Because you'll notice you did not get an E in your
Yeah.
answer.
Yeah.
I know it wasn't, I just like, that was just what.
That's exactly how I picture this one, yeah, it is a very E-friendly thing. So the blue and the green is not what they asked you to do, but had they asked you to draw one, this would be what I kind of came up with. You know, draw a path that goes through it, that's a good one. All right, so for part B, let's see. Part B, come up with the equation of the tangent line, y'all should have seen. You were freaking out, you're like, is it really, is that it?
I was like, change one, and then I was like,
Yeah.
10? And I was
Okay.
like, oh.
We need a point the point, was it -1, 2?
Mhm.
-1, 2. So they gave that to us, and then we needed to find a slope. So I will use the point -1, 2 in my derivative. -1's gonna make that a +1, 2 squared is 4, 4 divided by 2 is 2, so my slope is 2, giving me an equation, y minus 2 is equal to 2 times x plus 1.
Can you write like the dill something?
The what?
The like regular.
The general form?
Like,
Yeah. Y minus y1 equals m, x minus x1.
Okay.
That's the algebra 1 version. Our version is y minus f of x, or f of a, excuse me, is equal to f prime of a times x minus a. It's the same thing, but instead of using x1, y1, we use a, f of a, and then the prime notation to represent a
I was trying to read the
derivative.
signs. I think I get
You don't
mixed
like
up
the
with the
M's?
second X sometimes.
M is a ridiculous letter.
Yeah.
Well, okay,
What does it stand for? Mope.
but it's a fantastic question. What does M stand for? Yeah, for us it means slope, but math people are pretty logical. We don't get accused of being that creative. And if we pick
I
an
like
M in a
science.
problem, then the M meant something.
The most.
There are 3 classic theories. Number 1 is that M was the name of the person that came up with the idea, but that
Yeah.
the concept of slope has been floating around for so long that it doesn't really belong to anybody. It's not like somebody can claim it. The other one is the language that it came from. In Latin, monte, well in French, monte is to climb, and all the Latin languages would use that particular derivation of a word, so maybe to climb comes from the M word.
That
for
makes
I
sense.
didn't see that one.
And the other one is that it's a parameter. When you see x's and y's in a problem, you think variables. And when you see a's and b's in a problem, you think constants. Letters in the middle, l's, m's, and n's tend to be parameters, things that you are about to do to functions, kind of thing. So
I'm good
all
with the
3 are
Latin.
kind of, could be, but none of them have ever really been proven, so.
A1 doesn't seem that likely.
I'd go
The
with
second
Latin.
one seems like the
Yeah.
one.
Third one, I think, is just grasping. Back in the 70s, they were high and had to come up with another idea. This is the one that always gets me. Okay, you know what that is?
Yeah.
Yeah,
What is that?
that's our stupid formula.
Right, but which one is it?
Is it such?
Why?
Slope, intercept,
Intercept.
slope, intercept, okay? We're the only, I won't say only because I'm not exactly sure, but one of a handful of countries that writes that formula that way. Everybody else writes it like this,
I don't understand why we do that.
Because see the
because it's a
constant.
constant.
Why would we write P?
Or if we're gonna write b, why don't we call it ax plus b, because at least that would make sense. Okay, but we like to take things that work and just make it retarded
American.
stuff. Yeah.
American.
American, yeah. So, let's do this one so you can get to your quiz. Alright, the separation of variables part.
So did we invent the
We didn't
not-
make anything, we stole things.
no,
Yeah, we're wrong.
the non-metric system, what is it called?
Standard?
Standard.
Who made that?
You know, it's funny.
Yeah, who
We
did
did.
that?
You know, it's
That's what I'm
funny.
saying, we made that, like, why?
Do you know how many countries in the world use standard?
No one?
3.
Us?
Us,
Just Canada.
Liberia,
Oh, God, Brazil.
Burma.
Burma.
Yeah.
Where is that? That's fun to say.
Indonesia area.
Man, why don't we do metric system, make life so much easier?
It does.
It's
There's been a push every decade it rolls around. Why don't we do metric? Because, gosh, when I teach this to the Algebra 1 kids, they're like, well, our system is fine, I can handle it. And I'm like, okay, how many inches are there in a foot? And they're like, 12. I said, okay, so that means there are 12 feet in the yard.
No, what?
No, it's 3. Oh, all right, so bad example. If they're 12 inches in a foot, then
You
we
can't
use
come
that
up with a
same
good
logic,
example.
they're gonna be 12 ounces in a pound.
No.
No, there's 16. Makes no sense at all, our system.
There's just random numbers
None,
that-
yeah. And then going from
I
cups
need
to
cookies.
cups to pints to, or back and forth again, it's 2, 2, 2, and then you hit quarts, and it's 4
4.
quarts to a gallon, and why did you decide to switch
you
at
go,
that
you go
point?
ounces to cup, it's like 16, that's like 2, 2, a 4, and then it goes
2,
back.
2, 2, 4, and then that,
You might go have to know this next.
I hate it, I'm done with it, I hate standard, but I literally,
And then a
Do it.
teaspoon? Seriously? Or a pinch? And a dollop? I mean, seriously.
Just
What-
a dollop or a little sprinkle.
I literally do like,
Or-
I read the milliliters, I don't even do like, it's like, I'm like, how many milliliters does it need? Oh, that
Right.
many, okay.
Makes more sense. And the standard lets you convert. So if you are in, milliliters, which is volume, to cubic
Which is
centimeters,
meter.
which is distance, it's a direct translation, so.
It's the same thing.
You're just like, oh, hey, look at this.
They did a bunch, oh, and all I have to do is multiply or divide by 10? That's it? That's it?
A couple times, like, it's literally multiply and divide by 10 to the something.
Easiest system in the world, we can't get it right. At least we aren't using cubits anymore, I guess that's why.
What's a cube?
I don't wanna know.
Cubit was a system of measurement back in Egypt and ancient times, Babylon and Egypt
Yeah.
and stuff like that. It literally was the distance from the current king from his nose to his finger. So when you built something
That
like
changed
5
every
cubit,
year.
it changed depending on who.
Current
it
king.
All
was.
the time.
That's.
Like, I bet his arm or something, like, wasn't even, just the way he stood, just like, let me move just a little inch, and then you're done.
That's how you get yourself known. It's like how what king was you, how many it's king
Yeah,
it's
Wait,
king this guy's
wait.
cubit. Oh okay so it's,
Tuts cubit, like 5 tuts cubits.
and then it's like
Wow, already done?
Yeah, we'll just say this.
Woo!
no she's done.
Oh, you're done? Really? Sweet. Does your picture look like that?
Not without the drawing.
Yeah, forget the blue and green line.
Just the little dashes.
Her line's right.
Oh, except the moment. Maybe not.
You're on the right track with your antiderivative.
Ooh.
I will say, this is where it fell apart, right here. But I think after that, you did fine. You didn't finish solving, but you're more on the right track.
I want a Michael one.
Here's how it should have been done. Yeah. The good cubit.
A good cubit. I like it.
Separate the variables. So I will choose to bring the y's over, but I'm gonna leave the x and 2 together on this side. So I'm gonna get dy over y squared is equal to negative 1/2 x dx. I think that's the way most of y'all chose to do this.
Yeah.
Edward and Jerry actually brought the 2 over to the other side with the y. Did fine. It gave them a different c value because they had a different equation, but what they did was absolutely fine.
Oh, I have a question for you from Gabby. Well, actually, it just came up and so then it asked. Why do you wear your safety clip thing?
Because
Keep
of
you
you.
safe.
Thing?
What do you think safety pins are supposed to do? They keep you safe?
You never know. You know.
It's a probability
I
enhancer.
knew you told us one time, but I couldn't remember why, and so I was like, I'll ask him.
A probability in him to see me a lucky charm. I don't know.
Well, there's no such thing as luck, it's all
Yeah.
probability.
I was like, it's something kind of like
There's no
luck,
such
but
thing
then
as
I was like, but then again, he said something that wasn't luck, so I couldn't remember what it was.
Oh my god.
Alright, antiderivative of this is going to be negative